Welcome to today's session, and I want us to consider the topic of earthquake, and more specifically, I want us to look at this particular data, this one here. So this is the title is Global uh, Earthquake Tsunami Risk Assessment Dataset, and the overview is the Global Earthquake Tsunami Risk Assessment Dataset is a comprehensive machine learning ready dataset containing seismic characteristics and tsunami potential indicators for 782 significant earthquakes recorded globally from 2001 to 2022. This dataset is specifically designed for tsunami risk prediction, earthquake analysis, and seismic hazard assessment applications. Now, total records is 782 earthquakes, time period January 1st, 2001 to December 31st, 2022, that is 22 years. Geographical coverage, it's global, that is it covers from latitude of that shown, negative to that and that. File format, okay, that's not necessary for now, but we see that missing values none, 100% complete data set. Now, target variable tsunami potential indicator, that is binary classification. So key features in this data set, we have non-tsunami events are 478 records, that accounts for 61.1%. Tsunami potential events are 304 records, that accounts for 38.9%. Now, this data set, being that it is balanced, it is suitable for binary classification tasks. So these are the descriptions, and if you want to read more about this data set, you can visit this particular site as you see here, and that is where we begin our analysis. So I open up Jupyter Notebook, and there we are, and then I come here because this is the data set that I'm interested in. So what I'll do is I will, first of all, I will go to the download link and then I copy that. Once I copy it, then I get back to my Jupyter Notebook, I paste it there, then I run. Upon running, this is what I see. I see that it has now specified path to the dataset file, just as it is. So that allows me to continue with the rest of the analysis. And very quickly, I see that I need to import the libraries. So I'll start with import pandas as PD. Then I import OS. I import OS, after which what I'm trying to do is, being that I've specified the path to data set file is already specified, I want to use that then to load the data into the notebook. So having imported those two libraries, then the next thing I'll do then is to say dataset. Now we have to do that because you can't write two words in a row in Python. So by separating it, that communicates something. So I will say R, but then this R, I need to give it that, yes. Then I close it too. I need to close it. Yes, it's opened and closed. But in between, now I want to put this path here. I want to put this path here, that one. So I copy and then bring it here. Bring it in between, paste. Now I have that. And then the next thing I do is I want then to ensure that it is loaded properly. So I will write a few more commands. One is I will give an instruction that is print os dot list here. So I will specify the data set, the data, I specify the data path, I specify it is called the data set path, not just the data path, because that's what is specified up here. So it's the data set path as such. Once I do that, the next thing that I need to do is to then call, specifically say file path. We are still struggling with definition so that we have it loaded in our notebook without problems. So I will say os.path.join and then in bracket dataset path. I'm still not using the shortcuts. I just want to go the long way. Then comma. I'm specifying what I need. I need earthquake data, tsunami dot csv as such. Then next, then I'm now defining the data frame, which I'll now be referring to every time I'll be referring to this data set. I'll be referring to this data frame that I'll be using pandas to create. So it is df is equal to pd dot read csv read csv. But now because I defined the data set path to be the file path, here the data set path is this, but then I'd also said that the file path is the data set path. So here I can safely say in bracket file path. So that is that. The next thing that then I need to do is let me run it and see if everything is okay. Yeah, looks like all is well, because I can already see that the file path is already defined as the CSV that we had. So perhaps let me do the first test, that of looking at the first 5 entries in the data set, if our data is working, and we see that. So this exactly has worked, and we see that we have loaded our data into the notebook, and so we can proceed with our analysis. And so DF head just gives us an indication of what's in the data, and we see that the first column is magnitude, then we have CDI, MMI, all this, longitude, latitude, year, month, etc., whether there was an occurrence or not. So that's that. Another thing that we can assess very fast is looking at more of what we refer to as the attributes, like the number of columns in the data set, the types of data that are found therein, etc. So DF info gives us an overview of that, and we see that we have 782 entries, that is 0 to 781. data columns, as you see. And now we are good to go. And so data cleaning, just as we had seen in the preliminary, is not so so urgent now. So we can straight away move to the first bit of actually the main reason why I prepared this video. That is exploring the relationship between earthquake magnitude and depth. Exploring the relationship between earthquake magnitude and depth. So I'll proceed as follows. Probably okay, I'll run that. There's nothing in there now. So first thing that I'll do, because I'll be dealing with visuals, I need to import matplotlib.pyplot. So import matplotlib.pyplot as PLT. And notice that we had imported pandas, because pandas will be needed. So the only library that we were left with that is for visualization is this here. So that will allow me to bring in the aspects of visualization, so that we are able to see what the data pattern is. So first of all, what I'll do is PLT dot, I want to do a figure. So the figure is specified as such. So I say fig size is equal to, so in there is 8.5. So I'm specifying the width and height. Again, I'm also having another plot. PLT stands for plot. I'm plotting a scatter. Now I'm plotting a scatter. And this scatter, we are drawing our data from the data frame that we already had. And we are concerned with the depth. We are concerned with the depth. We are concerned with the depth. We are also concerned with the let's see. We are also concerned with the magnitude. Those are the two columns that we need. And then we specify alpha. Now this what this does is well, now the next one is color. And we have that, and we say dark red. We say dark red, like that. So we specify the color that we want to see come out of our scatter plot. Then the next thing, we also need to give title to this scatter plot. We have specified the dimension of the figure, which is a scatter plot, and now we need to give it the title. So we still say PLT dot title in bracket. Now we specify, in here we write the title of our chart. So we say magnitude versus depth of earthquakes. As such, now that becomes the title. So if we run that, which we are expecting to read that as the title, but again we need to label the x axis. So we'll still say PLT dot x label in bracket we specify, and here we have it as depth. So on the x-axis we have depth, and the depth is in kilometers. Depth is in kilometers. Depth is in kilometers. And y-axis, y-axis we have plt dot y label in bracket. Now here we call it the y-axis. We are now on the y-axis, which is the Richter scale. So magnitude, and we specify that it's measured in Richter scale. So that is yes, as such. So I have all those labels specified. Now, next thing is just for convenience, the following should come. So here we are tuning the grid in terms of visibility, etc. So true, we'll say true, and then we say line style, and that line style, we specify it as such. Alpha 0.6. So all this is about visibility. Then, of course, I want it shown. So I say show. So let's see if our code works. If it doesn't, then we'll see what to do with it, how to debug it so that it works. So we run. Upon running, we see that name PLT is not defined. Yeah, because I've not, I should run this once again. So what I'll do is to refresh, restart. So that is now okay. So I want to run everything. I want to run all cells so that this one is also captured. This PLT is also captured. Good. There we are. So what we see is magnitude versus depth of earthquakes. And this is a diagram that is a result of the data that we have just seen and interacted with. This one here, and you can check the link and also visit that site to see. These are data sets that are available, they're publicly available, and I'm making use of it to make more sense of what it is, to reveal the pattern behind it. And if you are, if this particular analysis is what you feel you need, then you should follow us. Visit datalyticsacademy.com. You'll be able to have a lot of choices where you can settle on what you want to do in future. There are a number of courses that I'll be listing or I'll be mentioning as we go by. But for now, because I didn't want to take much time, I want to continue with the analysis and sign off. So this is what we have. And particularly, the data set, what we see, the figure shows a scatter plot of magnitude versus depth of earthquakes, part of a broader global earthquake tsunami risk assessment study. Now, each point you see here represent an earthquake event plotted by its depth. You see, depth is here on the x-axis and magnitude Richter scale on the y-axis. Now, from this, we observe that most high magnitude earthquakes, those of 7 point and above occur at shallower depths. Occur at shallower depths, because if the depth is measured between from 0 to 700, but we see there's a lot of concentration of actually we see that most of the magnitudes beyond 7 are seen between 0 and perhaps somewhere nearing 100. So we see that most high magnitude earthquakes, that of 7.0 and above, occur at shallow depths of less than 100 kilometers. And again, deep focus earthquakes, those of more than 500 kilometer, tend to have moderate magnitudes, rarely exceeding 8.0. So if you look at this, then you see that rarely do they exceed. They're only beyond 8. We only see about 2 occurrences. So rarely do they exceed 8.0. Now the clustering near the surface here suggests that tectonic stress is more likely to release energy violently when close to the crust, where rocks are brittle. So again, this I leave to the experts to shed more light on, but this is what the data has revealed. As you have seen, we have picked the data as raw as it is, and from the analysis, this is what we see. Now, this pattern provides valuable insight into global seismic risks. Shallow, high magnitude quakes are often the most destructive, especially when occurring near populated coastal regions. I think this we have seen because much of the time earthquakes are reported. The pattern that we see is such that once one has erupted, then we see something like a ripple effect, and that confirms what happens with the tectonic plates. Now, again, in seismology, the relationship between magnitude and depth is crucial for understanding the potential for surface damage and tsunami generation. Now, shallow earthquakes, that is of less than 70 kilometers, often cause extensive surface damage. Now, intermediate depths, those between 70 to 300, those between 70 from here to 300 kilometer, dissipate energy before reaching the surface. Now, deep focus earthquakes, those of beyond here, from 300 going beyond, uh, rarely cause tsunamis, but offer important clues about subduction zone dynamics. Dynamics. Now, understanding these dynamics helps in building resilient infrastructure and improving early warning systems in earthquake-prone regions. Now, because this is part of the ongoing analysis in Datalytics Academy, this analysis is part of the Global Earthquake Tsunami Risk Assessment Dataset project, aimed at integrating geophysical data with machine learning and risk analytics to support predictive modeling. It's an excellent resource for students studying geophysics, environmental risk analysis, or earth science statistics. It's also relevant to policymakers assessing disaster preparedness and resilience, data enthusiasts exploring real-world natural hazardous analytics. Now, I cannot conclude this without acknowledging, passing some of the acknowledgements. This work was conducted by the Datalytics Academy, a digital learning and research platform empowering students and professionals in mathematics, economics, creative arts, and earth science analytics. Data was sourced from the Kaggle Global Earthquake Dataset, analyzed using Python, Pandas, matplots within JupyterLab, and the contributions and insight from the global data science community are also greatly acknowledged. Now, I want to stop there, but I hope you have seen this is an insight, and anyone who may be interested in delving much deeper into what this search data reveals, the pattern that it reveals, you can reach me so that we explore much of the richness of this data set. So up to there, I want to stop, and I hope to meet you in the next 1 hour. Thank you.